In this video, we're going to review lambda, which is our measure in this class for assessing nominal-nominal relationships. So once again, with a nominal variable, we have a categorical variable. For an independent variable, a categorical dependent variable. Lambda is going to help us assess the degree that those two nominal variables are related to one another. Lambda is what we call a PRE measure. PRE stands for proportional reduction in error. Now, the intuition behind a PRE measure is that if two variables are related, then knowledge of the independent variable should help us make, in some ways, accurate predictions of the dependent variable. So the way the PRE measure is set up, sort of conceptually, is that we're going to compare what our predictions would be if we didn't know the independent variable for y, and compare those predictions when we don't know x to our predictions we can make when we do know the values of x. In other words, what we're saying is that if knowing the values of x helps us predict y better than not knowing the values of x, we might conclude then that the independent variable is in some way correlated with the dependent variable. So what this means mathematically is that when we try to predict values of y not knowing the independent variable x, we're going to make some mistakes. We're going to make some errors. We're going to have some mispredictions. That's what we call the error. When we predict y knowing the values of x, we're probably also going to make some errors or mistakes or have some mispredictions. So the big question for a PRE measure is whether or not we are improving our predictions when we know the independent variable against when we don't know the independent variable. That is, if I make, let's say, 5 prediction mistakes when I don't know x, but only 3 prediction mistakes when I do know x, in this case, I've improved my predictions by 2, right? 2 out of 5, or 40%. Right? So in this case, what we're saying is that if my predictions improve, I can assess the degree of the relationship by that prediction improvement. So lambda takes on any value between 0 and 1, or 0 and 100%. And once again, the intuition here is that, am I making 0% improvements in my prediction by knowing x versus not knowing x? Or am I making 100% improvements in my predictions by knowing x versus not knowing x? In this case, if we're making 100% improvement, we would say, wow, that variable x is really correlated with y. You're improving your prediction by 100% knowing the second variable. Whereas if we have a lower value, let's say 0, right, the lowest value we can have, we're saying, well, you're not gaining any prediction improvement by knowing x versus not knowing x. And if that were the case, we'd say those variables are not related because we're not able to better show that a value for y can be predicted by a value of x. Now, I know a lot of this sounds a little bit confusing, especially when talking in the abstract. So let's jump into some examples to help solidify these concepts as you review lambda and your PRE measures.
All right, so let's take a look at an example of lambda so we can better get a sense of how PRE measures work. Here we're going to use the same question we asked earlier. Is gender coded as a simple dummy variable, male-female, correlated with course grade, also coded as a simple dummy variable, pass-fail? Remember, we're going to compare two scenarios. One where we know the dependent variable only, that is, the scenario without knowledge of the independent variable, against knowledge where we do know both the independent and dependent variable. So here, let's start with a crosstab. You can see in our first scenario, when we only know the dependent variable, that the crosstab is empty for male-female students. Here, we only know the distribution of the dependent variable, where we can see that 75 of the students have passed the course and 25 students have failed the course. There's a total here of 100 students. So looking only at the information we have in the table, what type of prediction would I make for a random student? Here it makes sense to pick the mode. In this case, the mode is pass. I would pick the mode because if I were guessing for a random student, I would be correct 75 times, and I would be incorrect 25 times. In this regard, since I'm incorrect 25 times, my prediction error is simply 25. Let's contrast the first scenario to our second scenario where we actually know the distribution of the independent variable. So here we have a crosstab, which may be produced from your actual observed data in your file, And here we can see that of the 75 students that have passed the course, 56 of those were male, 19 of those were female. Of the students that failed the course, 4 of those were male and 21 were female. That gives us a total of 60 males and 40 females. We asked the same question here for our second scenario. Based on the information, what would your prediction be, pass-fail, for a random student? The big difference is, knowing the independent variable, we can make a prediction or a guess for each category that we have for our independent variable. So here, looking at males only, we would predict pass, because pass is the modal category for males. In this regard, we would be correct 56 out of 60 times and incorrect 4 out of 60 times. Looking at the female column, we would predict that a female student would fail. Once again, we would pick fail because fail is the modal category for female students. We would be correct with our prediction for female students 21 times, and we'd be incorrect in our prediction 19 times. So, for our second table, our total prediction error is 4, the 4 mistakes we made for male predictions, plus 19, our 19 mistakes we made for female predictions, which gives us a total of 23 prediction mistakes. So now that we have our prediction error for our scenario where we didn't know the independent variable, and our prediction error for when we do know the independent variable, we can work on calculating lambda and understanding how a proportional reduction in error tells us that two variables are correlated or not. So here's our formula for lambda. Lambda is equal to prediction error without the independent variable minus prediction error with the independent variable divided by prediction error without the independent variable. Let's break that down a little bit. Looking only at the numerator, what we're essentially saying is, how much better is our prediction when we know the independent variable? So looking at our example, we know we made 25 errors in our prediction when we didn't know the independent variable, and we made 23 errors in prediction when we did know the independent variable. If we subtract our prediction error when we do know the independent variable from our prediction error when we don't know the independent variable, we can see that we've improved our prediction by 2 cases. That is, we better predicted our data by 2, knowing the independent variable than not knowing the independent variable. That number in itself, however, is not particularly useful because we don't know how many total prediction errors we have without using the denominator. That is, if we made 1,000 prediction errors, an improvement of 2 is not that big. If we made only 4 prediction errors, then fixing 2 errors is really big. So we need to then divide the numerator by the total number of errors we made without knowledge of the independent variable. By doing so, that tells us the proportional improvement we've made knowing the independent variable. So here, we know that our numerator is 2. We've gone from 25 errors down to 23, but we need to divide that by 25 because that was the total number of errors that we made without knowledge of the independent variable. When we do that, we get 0.08, or if we multiply that by 100, we get 8%. So our proportional reduction error is 8%. In this regard, we've improved our prediction by 8% knowing the independent variable versus not knowing the independent variable. Is 8% a meaningful reduction? Well, it really depends on how you view the world, but statistically, we would generally consider 8% to be evidence of a weak correlation. Let's take a quick look at another example. Does race affect political partisanship? Here there are 4 races, white, black, Hispanic, other, and 3 parties, Democrat, Republican, and Independent. I've only created the cross-tabulation here, but we can figure out the predictions for both cases without the independent variable and with the independent variable from our single table. If we didn't know the independent variable, we would look at the final column for total. We would guess that a randomly selected person would be a Democrat because we'd be correct 400 times, which is the modal category. That also means, however, that we'd be incorrect 600 times. We'd incorrect 350 times for Republicans and 250 times for Independents. Can we improve that prediction by knowing the independent variable? Once again, we're going to do the same thing except using full information from the table. We're going to make predictions for each category independently. Looking at the white category, we would predict Republican. We would be correct 200 times, which is the modal category for whites, but we make 300 errors, 150 mistakes for the Democrats and 150 mistakes for Independents. For the black category, we would predict Democrat because we would be right 100 times. However, we'd be wrong 50 times for the 25 Republicans and 25 Independents in this category. For Hispanics, we'd also predict Democrat. Here we'd be correct 125 times, but we'd be incorrect 125 times, as there are 100 Hispanic Republicans and 25 Hispanic Independents. Finally, for the other category, we would predict Independent, and we'd be right 50 times, but we'd also be incorrect 50 times, 25 for Democrats, and 25 for Republicans. That brings our total prediction error knowing the independent variable to 550. Now that we have our prediction errors, we can solve for lambda. In our numerator, we're going to take our 600 errors we made when we didn't know the independent variable and subtract our 550 errors when we did know the independent variable. That gives us a prediction improvement of 50 values, or 50 observations. We want to know what proportion that is of our total original error. So we divide our 50 improvements by our total error of 600, which in this case gives us an 8.3 proportional reduction in error. Once again, this is relatively low compared to some other cases, so we conclude that there's a weak relationship between race and political partisanship in this example.